Hello everyone, welcome to our first presentation for the weather and climate part of the workshop series. If you don't know my voice, my name is Malhar, and I, alongside Jack and Jake, made this presentation for weather and climate. So, before we get started talking about weather and climate, one of the most important things to understand and know how it works is the atmosphere. So, we're going to begin with understanding the atmosphere a little bit, exactly what is it, and we'll go on in later videos describing how the atmosphere affects weather and climate. So, at its core, the atmosphere is fluid. So, it's the region of space above the surface of the Earth, ranging from the ground all the way up until space. So that counts as the atmosphere, and you can think of it at its core as a fluid. So it moves in many ways like rivers, and it's this movement of the atmosphere rather than the atmosphere itself that generates much of the world's weather and climate. So many of you probably already know that the two main gases in the atmosphere are nitrogen and oxygen. There's about 71% of the atmosphere consists of nitrogen, and about 28% consists of oxygen. The 1% consists of things like argon, carbon dioxide, methane, and other trace gases. And essentially, you can think of the atmosphere as having mass as well. And by mass, more specifically, we mean that it exerts some kind of pressure on surrounding layers of air as well as on the surface. So this pressure generates heat, and heat causes air molecules to move faster, meaning the space between each increases. So the air becomes warmer and less dense relative to air around it, and as such, warmer air tends to rise. But as we know, as air rises up in the atmosphere, temperature drops as well. And as the air temperature drops, it becomes cooler and molecules slow down, causing them to become denser. And this cold air sinks. The process is very cyclical, and this is sort of the key driver in all of the Earth's weather. It's this movement of air, generally warmer air moving upwards and cooler air moving downwards. And the cooler air moves downward, as you can see, thanks to gravity. And so generally, as changes by elevation, less air that is above you as you climb up, right? That generally makes sense. And so it's interesting how some people who live at higher elevations actually have larger lungs and more red blood cells to accommodate for the lack of oxygen at higher altitudes. Generally, warmer air rises and has less pressure than cold air, which is heavier and sinks, meaning that lower elevations tend to have higher pressure and vice versa. You can see on this map below a map of the semi-permanent pressure systems in January, and we're going to explain the flow of air and this movement in greater detail, but you can generally see the areas of the Earth during this time of the year in January, where there are regions of high air pressure and where there tend to be regions of low pressure. So talking a little bit about the layers of the atmosphere. So beginning at the bottom, we have the troposphere. Troposphere is the lowest layer where most of the world's weather happens. And it's also the most turbulent layer as well. So the air currents and the friction that's sort of generated by the Earth's rotation creates quite a lot of turbulence. Moving upwards, we have the stratosphere. Basically, the stratosphere is dominated by two key factors. One is the jet stream and the ozone layer. And the jet stream are basically very fast-moving winds that exist during the stratosphere, and we'll explain more about them as we go on. And above the stratosphere, we have the mesosphere. Basically, in the mesosphere, it's a region where we see very rapid temperature cooling. Above that, we have the thermosphere. This is the widest layer of the atmosphere, At its maximum, it's about 480 kilometers thick. And the air pressure is very low here, but actually air temperature rises as the sun's rays pass through. So it's we generally find that temperature decreases as we increase in altitude, but in the thermosphere it tends to be warmer because of the effect of the sun's rays. And then we have the exosphere, and some people debate whether this is actually legitimate, a layer of the atmosphere. It's kind of just the boundary between Earth and space. And in addition to those main layers, we also have what's called the magnetosphere. And the magnetosphere is the layer of the Earth's atmosphere, sort of, you can see here, it sort of transcends the entire, all the other layers of the atmosphere, and actually extends quite a bit outwards into space. And essentially, this layer traps harmful energy particles that emanate from the sun, which we call solar wind here. You can see it kind of acts as a shield, protecting the Earth from a lot of the harmful radiation that the sun emits. And essentially, what the magnetosphere does is it traps these solar particles into sort of belt-like structure called the Van Allen belts, named after James Van Allen. And essentially, the interaction between the solar wind and the magnetosphere is what's responsible for generating the aurorae. The aurora borealis and the aurora australis, the northern and southern lights. I'll play a short video for you here.
Storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora. Earth.
So you can see just a short video there about how the aurora forms. You can see how that's basically just the interaction between solar wind particles and the magnetosphere. That's all for this video. Stay tuned for our next one.